Alright class, we are going to spend a little time looking at the arrangement of electrons in atoms. We are going to develop what is called electron configurations. We're going to do that in different ways. And I'm going to present this by showing you the different areas where electrons are believed to reside or hang out around the nucleus, and also show you how that corresponds to the periodic table. Okay, we're going to use several models in order to explain this, so stick with me. They all are related. Everything that we're going to talk about here relates one to another, and you're going to see patterns hopefully that you can repeat and also see how those patterns explain the arrangement of the periodic table. Okay, here we go. It is believed that electrons hang out around the nucleus in different areas or shapes or regions that are called now orbitals. Electrons don't orbit around the nucleus like planets around the sun. We know that's not true anymore. It was once believed to be true, but they more or less hang out in these regions, these areas that we call orbitals. They are high probability regions where you might find an electron. We don't know exactly where they are. We just know that they're most likely to be in certain areas around the nucleus. So let's say we have an atom, and this is going to represent the nucleus. And we know the electrons are going to be around that nucleus somewhere. We also know from experiments that were done using how light interacts with the electrons of a metal, and those electrons were excited when a certain amount of light, a certain amount of energy hit them, and only when a certain amount of energy hit them. We know that electrons reside at different energy levels, meaning they don't just hang out anywhere at any distance from the nucleus. They reside at specific kind of radii or certain distances from the nucleus. And we're going to call those energy levels. Within those energy levels, we have different shapes or different areas where the electrons are believed to hang out. So I'm going to do a couple models here. This model right here is going to represent the energy levels. The black dot in the middle is your nucleus, where your protons and neutrons are. And then the circles are going to represent the different energy levels where electrons are believed to reside. Each circle is representing a different energy level. So the first circle is the first energy level. And then we get the next circle out as the second energy level, the third energy level. And then we'd have the fourth energy level, and so on, as many as we need, depending on how many electrons there are. Okay? Within each energy level, there are different orbitals or shapes or regions where they can accommodate electrons. Each shape within an energy level can hold a maximum of 2 electrons. Let's look at those shapes right now. We're going to use a video to help us kind of describe and visualize these shapes. So here is an XY coordinate system, and it's just showing you an XY coordinate system so you can kind of orient yourself. The first energy level, the energy level closest to the nucleus, has one shape where the maximum of 2 electrons can hang out. Here's what that one shape looks like. It is a spherical shape, okay? Just like that. So that one shape right there, that spherical shape closest to the nucleus at the first energy level, we are going to call that 1s. 1 for first energy level, S for sphere. Okay? So we have 1s. That is the shape that is closest to the nucleus where the maximum of 2 electrons can hang out. You can have a maximum of 2. Okay? Then, once that has 2 electrons in it, it's full. The first energy level, that shape S, can only hold 2 and a maximum of 2, and once it does, no more electrons can be in the first energy level. No more electrons in the 1s orbital. You're going to have to go to the next energy level, the second energy level. Now, the second energy level is larger, further from the nucleus, so it doesn't just have a spherical shape, but it also has other shapes or other regions, other orbitals, where electrons can hang out. Remember, 2 electrons maximum per orbital, because electrons don't like to be close to each other. They repel each other. Okay, they like to spread out. And the further you are from the nucleus, the more space there is for electrons to hang out, and therefore more orbitals. So let's go to the second energy level. The second energy level, it also has a shape that we call S because it's spherical. You can have maximum of 2 electrons in that 2s orbital. Okay, so we have 2s is the next orbital that you can use when filling it with electrons. Okay, but at the second energy level, there's more space, so you don't just have a 2s orbital, you have what are called p orbitals, and there are 3 of them. They're going to be lined up or oriented along different axes. So this is the 2px, then you have a 2py. This is still the second energy level now. They're just different areas where electrons can hang out. And this is the 2pz. And you can have a maximum of 2 electrons in each of the p orbitals. So maybe one at one end and the other electron at the other end, something like that. There can be 2 electrons in this funny, kind of looks like a dumbbell or an infinity symbol, okay? That shape right there can accommodate 2 electrons. So can the other p orbitals. All right? So the second energy level doesn't just have s, but it also has p orbitals, and there are 3 of them. 2px, 2py, and 2pz. Now I am not going to keep writing the 2p's 3 times. I'm just going to write 2p, and you're going to have to know there are 3 of them, 2 electrons in each, for a total of 6 electrons in those p orbitals. Okay? Then, once we get to 2p, the second energy level is full. You can't put any more electrons, stuff them in there, because they won't want or allow that, because they want to repel. They're going to push the other electrons out further to the third energy level. Here's the third energy level. It has a spherical region. Okay, that's the first region in the energy level. It gets filled. It also has the 3 different p orbitals, 3px, 3py, and the 3pz. So it has exactly the same orbitals that the second energy level has, but also in addition to the s, the 3p's, it has some other shapes as well. We're going to get to that in just a second. So the third energy level has 3s and 3 different p's. Remember the 3px, 3py, 3pz, but we're not going to keep writing 3 different p orbitals. We're just going to write 3p, and that represents all 3 of them. Okay? When you get to the fourth energy level, the fourth energy level has, again, S, big sphere. It's bigger now, right? Further from the nucleus. And that 4s can accommodate 2 electrons. Now, as we get further and further from the nucleus, there are going to be more and more shapes. Now, we're going to have some other shapes come in here. Unfortunately, the number for these new shapes is 3. I know we're at the 4th energy level, but the number for that is going to be 3. These are going to be d orbitals. And the d orbitals, there are 5 of them, and these are going to be the 3d orbitals. Even though the 3d come in after the 4s, the d orbitals, the number for it is always 1 less than the row number of the periodic table. You'll see that in just a second. So after 4s, then we're going to start to fill the 3d, And these are weird looking shapes. There are 5 of them. And I'm going to show you how these shapes correspond to areas on the periodic table. 2 electrons in each of those shapes, only 2. 2 electrons in that shape, 2 electrons in this shape, even though there are 4 different kind of lobes there, only 2 in each of those shapes. There's 3 of them. Here's the 4th d orbital. And here's the 5th d orbital. This is 3d now, okay? So there are 5 different d orbitals, and I'm not going to write, even though there are 5 of them, I will no longer, after this, write 5 different d orbitals. I'm going to just write 3d, and you're going to know there are 5 of them. 2 electrons in each, 5 orbitals, 5 d orbitals. That's a total of 10 that can fit in all of the 3d orbitals. Okay? And then we would have also then for p, the 4th energy level also has p, and then we go on to the 5th energy level and the 6th and the 7th and so on. And I'll talk about those in a second. Okay? So we have these different areas where electrons hang out. Different energy levels, and within those energy levels, these shapes and these areas or orbitals or shapes, they increase as you move further and further from the nucleus. Okay? Now, let's do this. Let's look at our periodic table and pick an electron or pick an element and see what its arrangement of electrons would be and write out its electron configuration. And we're going to do them for a number of electrons, and you're going to start to see a pattern. Okay? Watch. Let's start with hydrogen. Hydrogen has 1 electron. That number right there above the symbol is its atomic number. It tells you how many protons there are in the nucleus. Hydrogen always has 1 proton. It's also going to be the number of electrons in a neutral atom of hydrogen. Okay? So, let's look at hydrogen. Hydrogen, its electron configuration is going to be 1 electron. And where is it going to be? It's going to be in the 1st energy level, closest to the nucleus. In what shape? 1s. So its electron configuration is 1s1. The 1s, the big one, means the 1st energy level. The s means the shape. And the small superscript 1 tells you 1 electron in that orbital. Let's look at helium. Helium has 2 electrons. Helium, 1s2. What does that mean? It means you have 2 electrons in the 1st energy level occupying what shape? The S shape, the spherical shape. Let's come over to lithium. Lithium has 3 electrons. Well, now you'll notice we're starting the 2nd row. Well, that corresponds to starting to fill the 2nd energy level. The 1st energy level is full. It is full after just 2 electrons. Once you have 2 electrons, remember there's only 1 orbital in the 1st energy level, 1s. Each orbital holds 2 electrons. So once you've got 2 electrons in the 1s, it's full, and any more electrons will have to be bumped up to the next energy level. So we are going to have, for lithium, 1s2, and then 2, 2nd energy level, s1. This is the order in which the orbitals get filled, 1s and then 2s. So now we have our 3rd electron at the 2nd energy level. Let's go over here to beryllium. Beryllium has 4 electrons. Beryllium, 1s2, first 2 electrons in the 1s orbital, it's full, then 2s2. Each orbital can accommodate 2 electrons, maximum. Okay? Boron, 5 electrons. Boron, 1s2, 2s2. You see how I just repeated that because the first 4 are going to go in the 1s and the 2s. And now I'm starting to fill the 2p orbitals. Remember, there are 6 of them. Or sorry, there are 3 of them. 6 total electrons in the 2p orbitals. So 2p, that's where our 5th electron goes. So far we have, for boron, we've got 2 electrons in the first orbital, first 1s orbital, and now we've got 3 electrons in the second energy level. Okay, 3 electrons. 2 in the 2s, 1 in the 2p. Let's go to carbon, 6 electrons. Carbon, 1s2, or 1s is full, 2s2, that's full. We're going to have to go to the p orbitals now, 2p, 2 electrons. Okay, we have a total of, there are 6 electrons represented there for carbon. That means we have, for carbon, we've got 2 electrons in the first energy level, and we've got 4 in the second energy level, in the 2s and the 2p. Let's go to nitrogen. Nitrogen has 7 electrons. Nitrogen, 1s2, 2s2, 2p. I need 7 electrons. There's 2, there's 3, 4. I need 3 more, and they're going to go in the p orbitals. Okay? So now I have 1 more electron in the second energy level. Oxygen, 1s2, 2s2, 2p4. How can I get all the way up to 3 and 4 for the p? That's because, remember, there are 3 of them, 3 different p orbitals, 2 electrons in each. 2 times 3 is 6. Okay? So now I've got 6 electrons, 1, 2, 3, 4, 5, 6 electrons in the second energy level. 2 here in the s, 4 more in the p's. Now we're on to fluorine, 9 electrons. Fluorine, 1s2, 2s2, 2p5. So that means in the second energy level, now we have 7 electrons. 1, 2, 3, 4, 5, 6, 7. Now we're at neon. 1s2, 2s2, 2p6. That's for neon. That's 10 electrons. And now you'll notice something. You've got 2 electrons in the first energy level. It's full. You've got 8 electrons in the second energy level. It is full. 8 electrons in the second energy level fills it. Every time you get to the end of a row, the highest energy level is full. And that means now if you've got more electrons, you're going to go to the next energy level, and that is the same as going to the next row on your periodic table. Every row is telling you what energy level are you filling. Okay? So the electrons have to get bumped out further from the nucleus to the next energy level. Let's do sodium. Sodium has 11 electrons. So sodium here, 1s2. You see, I just repeat all this, right? Just repeat everything that was for neon, and then just add on third energy level. We're up to what? We did the 1s, 2s, the 2p's. Now we're on the 3s. 3s1. That 11th electron goes into third energy level and starts to fill the s orbital. Magnesium, you can start to do these yourselves now. Okay, magnesium, what is that going to be? It's going to be 1s2, 2s2, 2p6, 3s2. Okay? Now, there is a repeating pattern here, maybe you're starting to discover it already, that corresponds with the periodic table. There are a couple patterns that I want you to recognize. One, every element in a column has a similar ending to its electron configuration. Let me show you what I mean. Hydrogen, right here, hydrogen, its electron configuration ends in S1. First energy level, S1. Look at the one right below it, the element right below it, lithium. It also ends in S1. The second energy level, but it still ends in S1. And right below that, sodium ended in S1, 3S1, but it's still S1. What does that tell us? It tells us that all of the elements in the first group, the first family, all have one outermost electron. Those are called valence electrons. So they all end, their electron configurations all end in S1. They have one valence electron, one outermost electron. In this case, for hydrogen, the outermost electron was in the first energy level. For lithium, the outermost electron was in the second energy level. For sodium, is in the third energy level, but they all have one outer electron, one valence electron. For the second group right here, the second group right there, they all end in what? Well, here's beryllium. It ends in S2. Okay? And if we were to do magnesium, oh, we did actually. We did magnesium, there it is, S2. All of these are going to end S2. They all have two outermost electrons. In the highest energy level, you've got two electrons. Okay? And you can see the pattern right here, ladies and gentlemen. Boron ends as S2P1, or you could just say it ends in P1, okay? But I'm going to put S2P1. It has three valence electrons, three electrons in the outermost energy level. So this group here is always going to end in S2P1. This group is always going to end in S2P2. And this group is going to end in S2P3. This one, S2P4. This one, S2P5. And this one is going to always end as S2P6. Now, sometimes there's going to be, as we get down here to these next rows, the fourth, fifth, sixth, seventh row, there's going to be, if I write them in the way they get filled, there's going to be a D in between those. But the important part is they're ending in the same, kind of the same number of valence electrons. So this group here has three valence electrons, this group has four, this group has 5, this group has 6, this group has 7, this group has 8, except for helium. Helium only has 2 outer electrons. That's why it is over here with the noble gases, because it's full after just 2. The first energy level is full after 2. So why is that important? It's important because when you look at this now, you start to understand, oh, that's why these elements in the same group, the same column, that's why they behave the same way. That's why they behave in a similar manner. That's why they're all in the same family. If they have the same number of valence electrons, when they start to interact with other atoms and other elements, they're going to react in a similar way, because it's those valence electrons that are part of the bonding and the reaction, which we'll talk about in the future. Okay? So if they have the same number of valence electrons, they're going to have the same or similar electron configuration, and they're going to have similar physical and chemical properties. Pretty cool. Okay? The other pattern that I want you to see is that here, you'll notice in these first two columns, we are filling the s orbitals. These first two columns are where you're starting to fill the s orbitals, whether it's the 1s, 2s, 3s, whatever row you're in. These two columns here are referred to as the s block. S block means this is where you're filling the s orbitals, either in the first energy level, the second, the third, the fourth, doesn't matter. This is the s block. Over here, you'll notice this is where we were filling the p, p1, p2, p3, p4, p5. This is where we're filling the p orbitals. Okay? And you'll notice for the s block, there are two columns in the s block. Why? Because the s orbital can hold 2 electrons. 1, 2. And then it's full. You have to go to a different orbital. So now we come to p. There are 3 p's, 3 different p orbitals. 2 in each for a maximum of 6. That's why there's 6 columns in the p block over here. 1, 2, 3, 4, 5, 6. This is where you're filling the 3 p orbitals, either in the second, third, fourth, fifth, or sixth energy level. Now I told you that there are d orbitals, and there are 5 of them. There are 5 different d orbitals. This is the region where we're filling the d orbitals. So we're filling the d orbitals here in this block right there. Okay? How many d orbitals are there? 5. 2 electrons in each. 2 times 5 is 10. Look what we have here. 10 columns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's where you're filling the d orbitals. Okay? Now the d orbitals, their numbering is a little bit different. Okay? I mentioned earlier that we start to fill the d orbitals here in the 4th row. Okay, here's our 4th row. Here's where we fill the 4s, and now we get into the d block. Unfortunately, the numbering is 1 less. You're just going to have to get used to it. The d block, the numbering for that is always going to be 1 less than the row number. So the d block, this is where we're filling the 3d. And then we start to fill the 4p here. Then we come back here to the 5th row. We're starting to fill the 5s. Then the 4d, d is 1 less than the row number, 5p, 6s, and then right here, ladies and gentlemen, the periodic table, actually the long version of the periodic table, these 2 rows down here should be inserted and the whole thing should be expanded. So these 2 rows actually should be in here and push the periodic table to outward a little bit. So this here after number 56 barium, we actually should come here to number 57. And this is your F block. This is where you're filling the 4F. Yes, I said 4. 4F in the 6th row. The F block is always 2 less than the row number. Sorry about that, just how it is. Okay? So we're still filling the 4F. Then we come back up here to the D block, 5D, remember 1 less than the row number, 6P, P is always the same as the row number, 7S, then we come down here to 5F, yes, 2 less than the row number, then we come back up here to 6D, 1 less than the row number, and if we needed it, we go to 7P, but we run out of elements, we don't have any more elements, so we don't need it, okay? So we've got the S block here. First 2 columns are the S block. The last 6 columns are the P block. And this middle bunch here is your D block. And this portion down there, those 2 rows that are sometimes pulled out, put below, that's your F block. Okay? And the number of columns in each block correspond to the maximum number of electrons that that particular orbital, that sublevel can hold. Pretty cool, okay? Now, let me show you one other thing here. There are some different ways that we can represent these electron configurations. I showed you the long version. And by the way, I'm going to show you also the order, the total order in which these orbitals get filled. Actually, I showed you already, okay? Let me just show you really quick. This is, just look at the periodic table and you'll know exactly the order in which the orbitals get filled. Here, first row, 1s, then 2s, 2p, 3s, 3p, 4s. Remember, d is 1 less, 3d, 4p, 5s, 4d, 5p, 6s. Then we come down here, 4f, 2 less than the row number, 5D, 6P, 7S, 5F, 6D, and we run out. Okay? If you want a little kind of model to help you remember it, besides looking at the periodic table, you can write them all out like this. Just adding 1 more letter to each row. Sorry, 4. I'm not going to need all of these. And then what you do is you draw diagonally across this list. I drew them like this and added another letter to each row, except down here for 5, 6, 7, because I don't need those. And I draw diagonally. So 1s gets filled first, then 2s, then 2p3s, then 3p4s, then 5d4p5s, and then 4d5p6s, then 4f5d6p7s, s7s, then 5f, 6s, and 7p. And that's exactly corresponding to the arrangement on the periodic table. Okay? So I should be able to give you any element on the periodic table, and you should be able to write the electron configuration. Okay? So for example, if I said silver right here, whew, silver, we could write the electron configuration for that. It's going to take a second, but we could do it. All right? Silver has 47 electrons. But we could write it all out. What would it be? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and then we get to here, and we are 1, 2, 3, 4, 5, 6, 7, 8, 9 columns into the D block, so that's going to be 4d9. And that would be it. Okay? Now, there is an abbreviated way to write these electron configurations, and I'll show you really quickly here using the noble gas symbol. So you'll notice we just keep repeating stuff, right? You can only use this abbreviation with the symbols of the noble gases. So for example, I notice here that sodium has everything that neon has plus the 3s1. Magnesium has everything that neon has plus 3s2. So the abbreviated version for sodium could be, I just write the symbol for neon. Remember, you can only do this you can only use the symbol for the noble gases. And then you add on whatever you need in the next row to give you the completion of that electron configuration for that element. In this case for sodium, 3s1. For magnesium, it would be everything that neon has plus 3s2. Okay? So if I wanted to do, for example, phosphorus. Phosphorus would be everything that neon has plus 3s2, and we're here 3 columns into the P block, so 3p3. There you go. One other way that I want you to be able to write these configurations is what's called the orbital notation. And that's basically putting a line or a box to actually represent the space where these orbitals are. And then I write the name of that orbital underneath it. And in this case, I am going to put the different p orbitals, 3 of them. Okay? So for example, if I wanted to do, I'll do 3p, 3p. Okay, if I wanted to do phosphorus, for example, here's how these orbitals get filled. Phosphorus, I have 15 electrons. 15 electrons. So here's how they get filled. The lowest energies always get filled first. So 1 electron, 2. And the electrons are going to be represented by arrows. If they're in the same orbital, I put 1 arrow pointing up, 1 pointing down, because they have opposite spins. The electrons spin, they're going to spin in opposite directions if they're in the same orbital. So the first 2 are going to go in 1s, then the next 2 are going to go in 2s, then I start to fill the p orbitals. If you're in a common sublevel, if you're filling all the p orbitals, you're in the second energy level, you spread the electrons out before you double them up. Electrons repel each other. They like to spread out. So my 5th electron is going to go in the first 2p, my 6th electron is going to go in the second 2p, and my 7th electron is going to go in the third 2p. Then if I've got more, which I do, I go back and double them up. So there's my 2, 4, 6, 8, 10, my first 10 electrons. The second energy level, the first and second energy level are full. That's because I'm here Neon, I have everything that neon has, and now I need to keep adding in order to get to phosphorus. I need, there's 10, I need 5 more. So there's 11, 12, 13, 14, 15. That's how I would represent the electrons for phosphorus in this orbital notation. Okay? All right. Hopefully this is helpful. You need to be able to recognize the orbitals. You need to know these different orbitals, S, P, D, F. You need to know how many of each there are at the different energy levels. You need to know how they correspond to the periodic table, that we've got the S block, the P block, the D block, and the F block. You need to be able to write an electron configuration, either the long version or the abbreviated version, and you need to be able to recognize the orbital notation. Okay? So that is our quick review, a concise explanation, hopefully, of the arrangement of electrons. And by all means, if you've got questions, let me know, and I'd be happy to answer them. All right. Thank you very much. Keep up the great work. Great job, you guys.